In this video, we're going to ask how we make fatty acids. This is the third in a set of videos about fats being used as fuel, so you might want to check out those previous two. But hopefully I'll give you enough context as we go that you can just jump right into this. And speaking of jumping in, let's do that. So how are fatty acids synthesized? That is our question. Quick orientation inside of metabolism. We are talking about a chunk of metabolism over here, which I'm circling, which is centered on the molecule acetyl-CoA. So everything that we see is going to be turned into acetyl-CoA or being made from acetyl-CoA in this case. And this network is centered on the citric acid cycle, which is occurring inside of mitochondria. In my past video looking at fatty acid synthesis, we asked how do we take fatty acids from the bloodstream, stick them into the citric acid cycle. In this video, we're going to say, hey, look, we've got some acetyl-CoA. How do we go backwards and turn them into fatty acids? So that's the plan for the day. That's what we're going to be talking about. If we think about this in terms of routes or roles of these different pathways, beta oxidation is used to release stored energy. That's to break fatty acids into acetyl-CoAs. What we're doing today is we're talking about making fatty acids out of acetyl-CoAs. How do we store energy for later? So let's do a quick rundown on what happens in beta oxidation, which breaks acyl-CoAs into acetyl-CoAs. An acyl-CoA is an acyl chain. This is basically a fatty acid that has been glued onto a coenzyme A, forming this acyl-CoA chain. And what beta oxidation does is you sequentially trim that acyl-CoA into acetyl-CoAs. So you take your if this is a C16 here, so it's got 16 carbons, you break that into 8 2-carbon chunks, right? We've broken it into 8 acetyl-CoAs. Turns out fatty acids are synthesized by basically the reverse of this process. So if we think about it, what we're going to be thinking about is how do we glue on 2-carbon chunks to build out a larger, longer molecule. So when we looked at beta oxidation, we did some calculations of yield, and what we found is for every acetyl-CoA, where you're doing the process of beta oxidation, you release 1 NADH, 1 QH2, and 4 ATPs, basically. Sorry, no, not and 4. I can't read my own slide. You release 1 NADH and 1 QH2, which if you convert to ATP equivalents gives you 4 ATP equivalents per acetyl-CoA. So this is keeping the acetyl-CoA intact, but just breaking all of the bonds between the acetyl-CoAs, you get 4 ATPs out. If you want to start gluing acetyl-CoAs together, what we'll find is it's going to cost us. It's going to cost an ATP just to do the gluing, and then it's going to take 2 NADPHs to do it, which, if you remember, the conversion factor here is 2.5 ATP per NADH and 1.5 ATP per QH2. You get less energy out of a QH2 because it enters the electron transport chain at complex 2 and doesn't pump as many protons as NADH, which pumps at complex 1. So you have 2.5 ATPs per NADH, 1.5 ATP for ATP, whereas this is 2.5 ATP per NADPH, right? This is basically the same as an NADH. And so overall, what this means is it's going to cost 6 ATPs to glue together an acetyl-CoA. So we get out 4 ATPs, it costs 6 to glue it together. So it takes energy to build this up. This isn't something that you can do for free. You have to invest energy to make a longer fat, which hopefully makes some intuitive sense. The ATP investment itself comes in using an ATP to prime acetyl-CoAs into something called malonyl-CoA. So what this does is it takes a bicarbonate and an acetyl-CoA. You invest an ATP. That yields an ADP in an inorganic phosphate and yields this molecule, malonyl-CoA, which looks a lot like an acetyl-CoA with a carbon dioxide glued onto it. So it's you've added a carboxylic acid onto the acetyl-CoA, making a 3-carbon molecule that you're then going to start gluing together. Now, what we're going to then do is we're going to do this entire assembly process on a protein called acyl carrier protein, which is a super cool protein. It's got like multiple arms that move together. Future video, I want to go through it in detail, but for now, we're just going to describe the process of what acyl carrier protein does. What acyl carrier protein does is you take a acyl carrier protein which has a free cysteine, an SH bond. You then glue on an acetyl-CoA acetyl group onto the acyl carrier protein. So you now made an acyl carrier protein, a protein that has an acetyl group hanging off of it, releasing your CoA molecule. The next step is I should say these carbons are going to be the tip of the acyl chain. So we're going to grow out from that, but we're going to grow out from this side. We're going to continually insert acetyl-CoAs between the ACP and the growing chain. So after this first priming step, which took an acetyl-CoA, every new carbon that we add is added with primed blocks of malonyl-CoAs. So here's what I just showed you. You've primed an acyl carrier protein with your acetyl group on it. Oops, we're now going to do a step where we take a malonyl-CoA. That looks like an acetyl-CoA with a carboxylate hanging off of it. And we're going to glue that here in between the acyl carrier protein and the other carbon atoms. So now 16, 15, 14, 13, we've glued those in between. The energy to drive that comes from this very favorable decarboxylation reaction. So when we primed our acetyl-CoA by making it into malonyl-CoA, we're priming that molecule to do chemistry to glue itself into this growing chain. So this is where the energy investment comes in. We're investing energy to drive this process forward. If you look through this, there's actually also quite a bit of, there's some redox chemistry that has to happen. That's why you have to involve some NADPHs. You need reducing power to drive this forward as well. Okay, so what we've done to this point is we've now made a 4-carbon acyl chain. We can then just keep going. So now we take another malonyl-CoA and we glue that in, and that generates our 12, 13 carbon, or 11 and 12 carbons. We can keep going with that. And you can imagine extending this ad infinitum until you get the chain that you want, the chain length that you want. Now, I really waffled on this. I felt like I could go into details on this and make this video very long, or I could not go into details and make this video very short. So I'm going to keep this video very short for now. But it turns out, I'll give a couple of quick teasers and then we'll be done. First is that palmitate, a C16 carbon, is the typical output of a fatty acid synthase, this whole acyl carrier protein business. And the reason it's a C16 is because there's actually a molecular ruler in there that as that chain grows longer, it basically hits the end of the pocket and then it's like, okay, and it falls off and it's done. It's a little bit stochastic. Sometimes you make a little bit longer, sometimes you make a little bit shorter, but overall, C16 is the average fatty acid that gets synthesized by this enzyme. The second thing that I am not going to cover now, but I just want to at least mention, is that there's a ton of modifications that can happen after this process, right? So this just makes a bog standard carboxylic acid with 16 carbons hanging off the end of it. There are a bunch of other enzymes that'll go around and will add double bonds. They'll add branching if you're in some weird microorganisms. They can do all kinds of crazy things to these chains. So there's a ton more chemistry that's available once you've built this base fatty acid that, again, I felt like getting into would just be going way down into the weeds too quickly. So look for future videos on that if you're interested, because there's some really cool chemistry and some really cool metabolism. But for now, we're just going to leave it and say, wow, there is a lot more to talk about with fatty acid synthesis. So overall, a quick, really high-level summary is that we synthesize fatty acids by the sequential addition of these molecules called malonyl-CoA. And this process is energetically costly and requires a lot of both ATP and reducing power, NADPH. So we're using NADPHs and ATPs. So basically, you can think about the conversion as every time we glue in an acetyl-CoA, it's going to cost us 6 ATPs. And when we pull that acetyl-CoA out later, we're only going to get 4 ATPs out. So we're investing energy to store fats, to store energy in fat. Okay. So that is what I have on fatty acid synthesis, sort of very brief introduction. Hopefully it was useful for you. I look forward to seeing you later as we talk about this in even more detail. But for my next video, I'm actually going to talk about the reciprocal regulation of fatty acid breakdown and synthesis. Hope you can join me for that. Until next time, I guess I will, you can do whatever you're going to do. I'm going to do whatever I'm going to do until the next time.